Hello and welcome to the wide world of physics, where today we're going to be looking at something just a little bit different. We're going to be looking at electrons specifically and how they're actually not only real, but they are very much matter. So in looking at electrons and how they affect us on a daily basis, we have to look at the history as to how they were discovered, what it means by their discovery, and how we can exploit that. How we can prove to ourselves more specifically that they are actually physical things. They're not some kind of magical, mythical, particle that doesn't really exist. They are physical things that we can use to our benefit on a daily basis. For that, we're going to need some considerably high-tech equipment, but before we get into the equipment bit, we have to have a bit of a history lesson. To begin our understanding of where we are now, we need to know where we were. We need to know the history behind all of this. So we start with 1803. Not a hugely long time ago in the grand scheme of some of the science we have talked about and will continue to talk about, but old enough to know that we've been looking at this for quite some time. We start with the work of John Dalton. Dalton was a very modest man who made his discovery, and he was a Quaker. He literally lived modestly for the rest of his life, even though he was quite notable for this discovery. In doing so, he came up with the idea that atoms will break down the same way every single time you break them down. So as you break substances apart, numbers of atoms may vary, combinations of atoms may vary, but they were all singular particles. That's where the revolution started. That is where we really need to start from. His work lasted for just over 100 years till we come to the next evolutionary step in our discovery. Approximately 100 years after Dalton's work, we have the work of someone called J.J. Thomson. Thomson revolutionized how we think of matter and how we think of materials by discovering a little piece of it. He refined the model, he built on the information that he had, and he made it a bit better by discovering electrons. Thomson knew that atoms were balanced. They were neutral particles, so they couldn't have a charge. Electrons are negative, and neutrons weren't even a thing. So there had to be some kind of positive thing. He didn't know about protons either, so there was this positive sphere, a soup, with some dots of electrons put into it. There are two ways to describe this. In the UK, it's described as the plum pudding model. In the US, it's often used as the chocolate chip cookie model. However you look at it, it's the same way. If you look at, say, a chocolate chip cookie, for example, you have the sphere of the cookie itself with chocolate chips dotted about it. That was Thomson's idea as to how atoms worked. He was wrong, but it was the next step. We had to go to how to get to where we are. And this is the next step involved. So, in a moment, we're going to look at how he had a look at it and how he came up with his idea. In order to perform this experiment, we are using a variation on what Thomson used to perform his actual experiments. He used a cathode ray tube, which is very similar to what you're looking at now. This one has some slight variances to it, but is very similar to the ones that he used. Now, for those of you old enough to remember, you will remember the old tube televisions and tube monitors, the ones that had the great big glass screen on the front of it. Now, you were told, way back in the day, not to sit too close to it. Well, there was a very good reason for it. You were told it was bad for your eyes, which, to a point, that's true. That's not actually why they really didn't want you to sit there. What they didn't tell you is that this side, on the end here, where the TV screen would normally be, will actually produce soft X-rays. So you were actually X-raying yourself if you sat too close to it. They don't go very far, but it's the reason I'm not standing on that end of the tube, because I would prefer not to X-ray myself. An additional reason why you can't do this at home is it requires a power supply that gets to 6,000 volts. most households will not have such a power supply, so it is something we have to do in the lab. So this is unfortunately something you cannot do at home. However, how this works is the silver part that you can see kind of in the middle of your screen is a electron gun. When you put a very high voltage across it, it literally fires out electrons through a coil. In doing so, it hits that screen which you see numbered 2 to 10. That's this bit here. That screen is coated in phosphorus and a couple other things, just like a normal TV screen was way back in the day. That will actually display the electron beam when I start firing it across. I've now zoomed in so you can see a bit better what's going on. So as I turn it on, you'll be able to see a light that comes on here. That's the electron gun being charged up. As I give it the full 6,000 volts, you should be able to see a blue line that has now appeared going across the middle of the screen. Now that blue line is literally electrons being fired across at very high speed towards that blue paper. Now, the thing about Thomson is he wasn't entirely sure what these things were, but he proved it to himself the way I'm going to prove it to you now. He used a magnet. Now the magnet I'm using is this thing called a Helmholtz coil, but as I bring it near, you can physically see that the electrons are diffracting. They are literally being spread apart and pushed away. Now the thing about magnets is they're very specific in the fact that they will not work on anything that isn't matter. You can't force something that isn't physical to move with a magnet. So if I'm moving that beam, it can't be light, it can't be a wave of any kind, it can't be anything that isn't physically there. It has to be matter. When we zoom in a bit more, you should be able to see that there's a nice concise beam, nice bright blue beam, that if I then get closer with a magnet, you can see it moving away. You can see it wanting to move. Well, it actually physically does move. The reason it moves up and down like that is purely because this magnet is circular. It's a round magnet, and when I generate the magnetic field, it is not a normal magnetic field like a regular magnet. But this proves the point incredibly well, because you need quite a strong magnet to do this, but the fact that it's moving shows that that blue beam is not a laser, it is not light, it is physical. It has physical properties, it has mass. Electrons have mass. It's not big, but it has mass. They're moving so fast, though, that as you get closer to it, you can see that they're moving further and further away. They're deflecting from the source. As I move it towards the source, you can see I can get it to go even further. The point being that as this happens, those are physical quantities. It's a physical thing, it has mass, it is physical, it is real. And that changed how we think about what we're made of, what everything is made of, and how we understand the universe. Thank you very much for watching. I hope you enjoyed learning about the history of the atom. I hope you learned something about electrons themselves and how they've gone to revolutionize our lives and how we can eventually start to use them in things like electricity and electromagnets to improve our lives. If you would please make sure to like and subscribe to this channel so that we can continue to produce additional content for you. Thank you very much.